There is something called a steric effect, and we will see what that means. So we wrote this relation between the density variations and sea level variations, h over rho ref times the magnitude of the horizontal gradient of the averaged density is approximately equal to sea level gradients. Okay, if you have hydrographic data for density, then you can compute sea level variations. That's what it means as well, right? So in this case, delta eta over h can be written as alpha t times t minus t0 minus beta s times s minus s0. We carry the angular brackets to still imply that they're averaged over a certain depth. We are implying. This is just saying that we can approximate the ocean density as a linear function of thermal expansion and salinity coefficient and the changes in temperature and salinity with respect to a reference temperature and salinity. So here the angular brackets are still 1 over h plus eta. That's the total water column from h from the bottom to the top, and the integral minus h to eta. Z is going down, so we go from minus h, and eta is typically above the surface, so we write it as positive, but obviously it can also be below the 0z, right? So then whatever quantity you are trying to average in the integrate in the z direction. Okay, so sigma is sigma 0 plus rho ref times minus alpha t times t minus t0 plus beta s times s minus s0. We can see that we keep flipping these signs, but the main thing to remember is that salinity increases density and warmer temperatures decrease density. That's why we have these signs being carried along. Okay, so if we estimate the contributions to sea level change by temperature and salinity, typical numbers, temperature tends to, if it warms, it tends to increase the sea level, whereas if salinity increases, it increases the density, which reduces the volume and it lowers the sea level. Okay, so that has an opposite effect. So it tends to compensate for sea level, and this can be a serious contribution in some places like the Pacific and the Southern Ocean. But in general, temperature effects dominate, as you can see here. Okay, so just to remind ourselves, let's look at the structure of the potential density that we have looked at already a couple of times. Top 1 kilometer and from the surface to the bottom, and zonal average salinity showing our top 1 kilometer and the total water column. So this is the steric effect, often referred to as thermosteric and halosteric effects. Okay, so under global warming, for example, you can have contributions to sea level rise just from temperature change. Global warming is obviously warming of the atmosphere, but the ocean is taking up more than 90% of the greenhouse related energy being produced by the humans. So the oceans are warming, which means sea level is rising, but it doesn't rise everywhere because there is dynamics which are still controlling the patterns. And salinity is increasing in some places where evaporation is increasing. Remember, warmer atmosphere can hold much more water vapor because of our Clausius-Clapeyron exponential relation. But there are also places where rainfall is increasing, so then salinity is decreasing. In fact, on long time scales, the changes in hydrologic cycle of the atmosphere can be estimated by looking at changes in surface salinity. That's how good a meter that is for changes in atmospheric water budget changes. Okay, so that's the steric effect, and this was our compensating effect between the deep ocean pressure gradient and sea level pressure gradient to produce near zero currents at depth. Is there another way to do it? There is. It's called the dynamic method. So if we go back to our thermal wind relation in terms of sigma, we had dug dz and dvg dz as g or f rho ref d sigma dy minus d sigma dx. Sigma is of course our rho ref plus sigma, and we had written in the vector form as minus g or rho ref z hat cross grad sigma. What are we going to do with it? We're going to see if we can estimate sigma using let's say hydrographic sections we have. Either you have altimeter data for sea level and you can estimate geostrophic surface currents, or you have hydrographic data from ships and so on, and we can estimate what is called a dynamic height and then geostrophic currents. So in this case, it turns out that if you integrate, for example, the x component of this from z to z1, so let's say z1 is a reference surface which can be made deep enough so that the current there is zero. Okay, then you can integrate this d sigma dy g or f. Rho ref is a constant anyway, z1 to z, 1 over rho ref d sigma dy dz, where the quantity dynamic height here is defined as basically the integral of z1 to z sigma or rho ref dz. So it's a normalized density height. Okay, so if you integrate from z1 to z the ratio of sigma or rho ref, where rho ref is constant, so basically the isopycnal variation in the vertical determines the dynamic height, which is slightly different than the sea level, but for most practical purposes they are the same. Why? Because sea level is the entire water column, whereas dynamic height is between two height levels, from some z1 to some z. Why is this important? As I said, if you have density data or just sigma data from some other source than the sea level from altimeter, then you can assume a deep level of no motion and still derive the geostrophic currents. So in this case, if you choose z1 to be deep enough, then ug z1 will go to 0 and you will still get surface geostrophic currents, just like we got it from d eta dy. Instead, we are integrating density and defining a dynamic height, which is closely related obviously to the sea level. So the density structure of the ocean determines the dynamic height as well as the free surface. They are closely related. Okay. Does it work? So let's look at this cross section here across the Gulf Stream in the Atlantic at some latitude. I think it's at 38 north, just before, just after the Gulf Stream separates off. So you're looking at going from the boundary at 73 west to about 69 west, eastward, and you have the strong Gulf Stream here, and the isothermals are going here into the open ocean, where you're basically at the edge of the subtropical gyre. So you can see the deepening here, and the salinity variations are shown here. Again, high salinity in the subtropical region, even though we are almost at the edge of it. And dynamic height computed with the information is given this way. So what is happening? You have dynamic height varying from west to east, and you can use your d sigma dx to see if you can get estimates of the geostrophic currents. So G or F at 52 degrees whatever this unit is. Okay, 2 omega sine 52. That is our F. The dynamic height difference is about 1 meter. Okay, and the width is about 100 kilometers, and you get a speed of about 0.85 meter per second. So the Gulf Stream, even though it's a boundary current, is it really in geostrophic balance? Well, once it peels off and goes into the open ocean, remember before we looked at the sea levels, the Coriolis would be acting to the south and pressure gradient is acting to the north. So you think about d sigma dx being related to V. So you have a geostrophic current of 0.85 meter per second, which is quite a good estimate for measured Gulf Stream velocity at that point. Okay. Long story short, the geostrophic balance does work done with this dynamic height method. Okay, so you don't always have a satellite when you go beyond about 1993 or so, when the first long-lasting altimeter mission got launched. There is an older one as well, but there is not much good data from that. But you have a lot of hydrographic data from before. So you can use the hydrographic data with the dynamic height method to estimate geostrophic currents. That's the main message. Okay.